Drone racing is a thrilling and fast-paced sport in which pilots control small drones using a live video feed from the drone's camera. The objective is to navigate the predefined course and pass through all of the gates in the correct sequence, faster than any of the other competitors. It is a test of skill, strategy, and quick thinking, as the pilots must maneuver their drones through the challenging racetrack at high speeds. In this work, we present Swift, the first autonomous system to achieve champion-level performance in drone racing. Swift won multiple races against the champions of 3 different drone racing leagues and achieved the fastest recorded race time. All of this, while only relying on an onboard computer, a single camera, and an inertial sensor. Swift uses visual inertial odometry, also known as VIO, to estimate its own position, velocity, and orientation. While such an approach produces accurate estimates when operating in near-hover conditions, these estimates substantially degrade at the speeds encountered during drone racing, as shown in green. To improve the estimation quality in such agile regimes, Swift complements the estimate from the VIO pipeline with a learning-based detection system that segments racing gates in the images captured by the onboard camera. Given the position of a gate in the world frame, Swift uses the PNP algorithm to triangulate its location. The animation shows one or more gates being detected during a flight. Swift uses a Kalman filter to combine the estimates from the VIO pipeline with the pose estimate obtained from the detected gates. The uncertainty of the estimate of the PNP algorithm decreases quadratically with the distance towards a detected gate. As a result, the variance of the Kalman filter posterior also decreases when approaching a gate. Racing a drone at high speeds through a complex track requires quick and precise control actions. This is especially challenging when using a camera for state estimation, which produces noisy estimates of the drone's state. To overcome this challenge, Swift uses a learning-based control policy that directly maps noisy state estimates to control commands, allowing for rapid and accurate steering of the drone. The control policy is represented by a neural network and is trained via deep reinforcement learning in simulation. During the training process, the control policy explores the environment using 100 agents in parallel and finds faster and faster paths through the track layout. The entire training process takes less than 1 hour on a normal desktop workstation. To prepare the control policy for the noisy and imperfect state estimates available on the real system, Swift uses flight data collected in the real world to identify residual models for perception and dynamics. These residual models capture effects that are difficult to model in simulation, such as the degradation of the vision-based estimator or turbulent aerodynamic effects. Swift uses this augmented simulation to fine-tune the control policy for real-world deployment. This results in a highly competitive policy that can cope with the uncertainty of the real system. We benchmarked the performance of Swift against some of the best human pilots in the world. Swift raced against Alex Vanover, the 2019 world champion of the Drone Racing League. Thomas Bitmata, the 2-time multi-GP International Open World Cup champion. And Marvin Schapperer, the 3-time Swiss national champion. When comparing the trajectories flown by the humans and Swift, we notice that the autonomous system is more consistent across laps and is able to take tighter turns. This gives it a decisive advantage in a race. Swift won multiple races against each of the human champions and achieved the fastest recorded race time. This marks the first time that an autonomous mobile robot has achieved world champion level performance in a real-world competitive sport.